Sound waves calculations. Physical Sciences grade 10. At the end of this lesson, you will be able to use the expression for speed v equals to the distance x, all of it divided by the time taken, and the wave equation, which is equals to the speed v equals to the frequency f multiplied by the wavelength lambda. And we're going to use these equations to solve problems involving echoes. For example, we will look at how ships in the ocean use a process called sound navigation and ranging, or SONAR, to determine how deep the ocean is at a given point. Moreover, we will learn how birds and dolphins use the reflected sounds or echoes to form a picture of their surroundings, and this process is referred to as echolocation. Question 1. A ship sends a signal to the bottom of the ocean to determine the depth of the ocean. The speed of sound in seawater is 1,450 meters per second. If the signal is received 1.5 seconds later, how deep is the ocean at that point? We are given the speed of sound, that the speed of sound in seawater is 1,450 meters per second, and that the time it takes for the signal to be sent and to come back to the ship is 1.5 seconds. In the last video, we learned that sound waves can be reflected by large surfaces such as the walls of buildings. And as such, sound waves can also be reflected deep within the ocean by a seabird. Hence, ships on the ocean make use of the reflecting properties of sound waves to determine how deep the ocean is at that point. The image on your screen demonstrates how a sound wave is transmitted by the transmitter this is the transmitter of the ship, and this sound wave is directed towards the seabird, where it bounces off, and then it is directed towards the receiver on the ship. Because we know the speed of sound, in the last example they said the speed of sound in water is 1,450 if I'm not mistaken, and that the time taken from the sound wave leaving the transmitter towards the seabed where it's reflected and coming back, that entire time was said to be 1.5 seconds. We know the time, we know the speed, it means we can actually determine the distance x, and this distance x will tell us how deep the ocean is. And this process of doing this, of using the reflecting properties of sound, is called SONAR, or sound navigation and ranging. The distance from the ship to the bottom of the ocean can be determined using the expression for distance, which is that the distance x equals to the speed v multiplied by the time taken. So if we know the speed as well as the time, we can determine the distance. The distance is measured in meters, the speed is measured in meters per second, and the time is measured in seconds. So from question 1, we read that the speed of sound in the ocean is 1,450 meters per second. The time taken for the sound wave to leave the transmitter at the ship, hit the bounce off the seabed and get reflected, and finally reach the receiver at the ship is 1.5 seconds. The round trip from the ship to the seabed back to the ship again is 1.5 seconds. However, we are not interested in the round trip the sound wave takes. We are interested in the trip that the sound wave takes from the ship to the seabird, because we want to calculate the distance from the ship to the seabird. So, if the distance from the ship to the seabird is equal to the distance from the seabird to the ship, and the speed is constant throughout, then it means that it takes half the total time for the sound wave to travel from the transmitter of the ship to the seabird. Therefore, the time from the transmitter to the seabird is equal to 0.75, which is half of 1.5 seconds. So I just said 1.5 divided by 2, which was equal to 0.75 seconds. Using this information, we need to find the distance x from the ship's transmitter to the seabed, which will tell us how deep the ocean is at that point. So to solve, we use the relation x, or the distance x, equals to the speed v multiplied by the time t. Substituting the known values of the speed, which was 1450, and the time taken for the sound wave to travel from the ship's transmitter to the seabed, which we calculated or we determined as 0.75, we have that the distance x equals to 1450 multiplied by 0.75, right? And this means that the ocean at that point is 1087.5 meters. You see, by just knowing the speed of sound in the sea or in seawater and the time it takes for the sound wave to travel from the ship and then return back to the ship, we can actually determine the depth of the ocean at that given point. So sonar is something that is used to determine the depth of an ocean at a particular point using sound waves. Imagine if you could see without using your eyes. That would be very cool. Echolocation refers to seeing without sight. Animals like dolphins and birds make use of sound waves to see or find their way, and also to find food. Just like ships on the ocean, as with our last question, dolphins use sonar to navigate. That is, dolphins use sound navigation and ranging to navigate. Let's say we had a dolphin and Nemo. The dolphin sends sound waves to Nemo, and these sound waves are reflected off Nemo. Then the dolphin uses the reflected sound or sound waves to form a picture of Nemo, like Finding Nemo. This is called echolocation. The sound waves produced by dolphins has a very high frequency, as you will see in the next question. Sound waves with very high frequency are called ultrasound, and we will talk about ultrasound in another video. Question 2. A dolphin emits an ultrasonic wave with a frequency of 0.15 megahertz. The speed of the ultrasonic wave in water is 1500 meters per second. Calculate the wavelength of this wave in water. To calculate the wavelength, we are going to use the wave equation, which expresses that the speed of sound v of a wave is equal to the frequency of the wave times the wavelength of the wave. The speed is measured in meters per second. The frequency f is measured in hertz, and the wavelength lambda is measured in meters. We are given the speed of sound of the sound wave as 1500 meters per second and the frequency as 0.15 megahertz. And we have to determine or find or calculate the wavelength, and that wavelength must be calculated in meters. So the SI unit for wavelength or lambda is meters. What do we need to do? This means that we first need to convert something. We first need to convert the frequency f from megahertz to hertz. 1 megahertz, and this is something you should keep in mind, 1 megahertz is equals to 1 million hertz. Another way of writing a million is as 10 raised to the power of 6. This means that 1 megahertz equals to 10 raised to the power of 6 hertz. Meaning we have, or in this instance, before I jump ahead of myself, if you look, this would actually mean that the letter or mega, which is represented by the letter capital letter M, is actually just equals to 10 raised to the power of 6. So every time you see mega, just know that that prefix stands for 10 to the power of 6. I will do a video where we just talk about prefixes to units. So where were we? So if we continue to convert, we will say that 0.15 megahertz equals to 0.15 multiplied, so in the place of mega, we multiply by 10 to the 6 or 10 raised to the power of 6 hertz. And if you put that in your calculator, you'll find that 0.15 megahertz equals to 150,000 hertz, right? So now that we have the frequency in the right units, we are ready to solve. And we said that we would use the expression for the wave equation to solve for the wavelength. So the expression for the wave equation, we said it is that the speed v equals to the frequency f times the wavelength lambda. We need to make the wavelength the subject of the formula because that is the quantity that we are trying to solve for. How do we do that? One way of doing that is to divide both sides of the expression of the equation by f. So we will divide the left hand side of the equation with f. So meaning on the left hand side we have v divided by f, which is equals to what is on the right hand side is that the frequency f multiplied by lambda divided by f. On the right hand side you can just see that f divided by f is just 1, meaning on the right hand side you will only be left with lambda, but on the left hand side you will still have your speed v divided by f. I hope that is clear. Now this means that the wavelength lambda is equals to the speed v divided by the frequency f. Now, by substituting the known value of the speed, which is 1500, and we divide it by the known value of the frequency, which is 150,000, we can actually get that the wavelength lambda equals to 1500 divided by 150,000, which is equal to 0.01 meters. Therefore, the wavelength of this wave in water that the dolphin sends out is equals to 0.01 meters. That was a very interesting question. So let's move on to another question. Calculate the frequency in hertz and the wavelength of the annoying sound made by a mosquito when it beats its wings at the average rate of 600 wing beats per second. Assume the speed of sound waves is 244 meters per second. Mosquitoes beat their tiny wings so quickly that they produce that zzz sound that we are all familiar with. This beating of the wings is so quick that in just a second, in 1 second, it has done like 600 of those beats. The frequency in this case is just going to be the number of beats in 1 second, or the number of beats per second. We have that the number of beats in 1 second is 600. This should tell us that the frequency is actually just 600 hertz. So we were given that the speed of sound is 244 meters per second, and we've just determined that the frequency f equals to 600 hertz. What we need to find is the wavelength, and that wavelength must be in meters. To solve this problem, we again use the expression for the wave equation. In the last question, you saw how we can rearrange the quantities in this expression, so I'm not going to repeat it now. So we have that the wavelength equals to the speed divided by the speed v divided by the frequency f. And if we substitute the known values of the speed and the frequency, we find that the wavelength equals to the speed, which is 344, divided by the frequency, which is 600. You put that in your calculator, you'll find that the wavelength of this sound made by this annoying mosquitoes while you sleep at night is actually 0.57 meters. Therefore, we can say that the wavelength of the annoying sound made by the mosquito is 0.57 meters. In this lesson, we have used the wave equation, which is v equals to, or the speed v equals to the frequency f multiplied by the wavelength lambda, and the wave speed equation, or the speed equation, which is that the speed v equals to the distance x divided by t, to solve problems related to the use of sound navigation and ranging, or SONAR. We've also learned that birds, dolphins use also this sound navigation and ranging to navigate their surroundings, and this process is called echolocation. In the next video, we will talk about characteristics of sound waves. What I mean is that you will learn that sound has something called a pitch, a loudness or a volume, as well as a tone. And we will talk all about that in the next video. So please watch it as soon as it is uploaded. Thank you so much.